Butler-Ulmer model of electrode kinetics. In this lecture, we will discuss the equilibrium condition, in which preferably we will discuss the exchange current, that is the implication of the current potential characteristics, which have been discussed earlier in the previous lecture. By discussing this detailed picture of the effect of the potential change on the free energies of activation for oxidation and reduction. While discussing this diagram, we have considered that at the equilibrium condition, the net current is zero. We require electrode to adopt the potential based on the bulk concentration of the oxidized or reduced species, as directed by the Nernst equation. The current potential characteristic derived was using the transition state theory, in which we have derived expressions for the exponential terms of the free energy by incorporating the transfer coefficient, and we have derived the expression giving the standard rate constant. So let's see what was the expression. So here I is the total current generated with application of the applied potential, and IC is the cathodic current that is generated due to the application of negative potential, and IA is the anodic current that is generated with application of the positive potential. But here the IC and IA are both positive terms because they are the current terms, but direction is inverse for each other. For equilibrium condition, we have derived afterwards that the rate of forward direction is equal to the product of the rate of standard rate constant into an exponential term that is representing the transfer coefficient and the number of electrons that are transferred in the redox direction. F is a factor showing the Faraday's constant over the RT. So here we have E that is applied potential, and E naught dash is the equilibrium potential. So here we have two rate constants that are rate of forward direction and rate of backward direction, which have been derived using the application of the external potentials. Now again consider the equilibrium condition. The net current is zero when the cathodic current and anodic current have equal contribution. As the rate of forward direction and the backward direction are equal, then the total current is zero, that is equal to the I. So we can write the expression by comparing above three equations, in which this one is showing the net current that is generated with application of the potential at the surface of the electrodes, where this rate of forward and backward directions are given by these expressions. So by combining these three expressions at equilibrium condition, when the total current or the net current is zero, when these two terms are cancelling the effect of each other. So here we have 0 is equal to the current. So here we can put the value of this term with the values of Kf and Kb from these two equations. So we get the equation K naught is the standard rate constant, and here we have the concentration term, that is the concentration of oxidized species at the surface of electrode at particular time, and this term is common with the standard rate constant with this exponential term which is related to the rate of forward direction. So minus alpha is the transfer coefficient. So here as I have expressed the f in terms of f over RT, so this term should be, this one should be the Faraday's constant. So here we can write this term as in terms of the constant f. So here we have in this equation we have expressed the equilibrium condition, that is the net zero current condition. So we require here to involve the bulk concentrations of the oxidized and reduced species also, as this equation is expressing the current in terms of forward and reverse or the backward rates only for the concentrations that are at the surface of the electrode. This 0 is actually the x, which is the distance between the actually from the surface of the electrode, from the this surface to the towards the solution. So at the surface of electrode this x is 0, and at any position near the electrode the value is x. That is the bulk concentration of the oxidized or reduced species. So the first equation, which is the equation number 1, we can rewrite this equation at this term, this whole term is equal to 0. Then we can rewrite this equation as written here. So here C naught at 0 T is the concentration at the surface of the electrode for oxidized species, and concentration of the reduced species at the surface of the electrode. So here we have considered that the this condition is equilibrium when the net current is 0. Again this potential will change to the equilibrium potential, and E naught is the actually standard electrode potential at equilibrium, and E is the equilibrium potential. So we are going to call it equilibrium potential. So the current potential characteristic derived here does not yield the thermodynamic relation for the species, which also incorporating the bulk concentration. So now let's first simplify this equation. So here these are the common terms which can be cancelled, and we can modify this equation as this species, that is the concentration of the oxidized species at the surface of the electrode over this term, that is the concentration of the reduced species at the surface of the electrode. So here we have to divide this factor with this one. So we have the factor that is minus alpha NF E equilibrium minus standard electrode potential at equilibrium condition. From this part, and by multiplying with 1 we get another exponential term that is minus only 1, so we can write alpha that is actually coming from here. And for this one we have another term that is showing the 1 NF E equilibrium minus standard electrode potential at equilibrium condition. So these terms are cancelling. So here we have the simplified equation, that is the ratio of the concentration of the oxidized species at the surface of electrode over the concentration of the reduced species at the surface of the electrode is equal to the term. So here F is the constant, that is the Faraday's constant over RT, and the equilibrium minus E naught dash. Since equilibrium applies, the bulk concentration of the O and R are found also at the surface. So here this reaction is taking place at the electrode surface, and it is also in equilibrium with the bulk concentration. Let's we have electrode surface. So here the oxidized and reduced species that is present at the surface is also in equilibrium with the bulk concentration. So we can consider this equation as the bulk concentration for the both species. So we can consider this concentration that is in equilibrium with the bulk. So we can write the concentration that is represented as star is the bulk concentration, is equal to the by taking the log natural of this equation in both sides, so this term is cancelling. So here we have log natural of C naught star over CR star is equal to so here F is the factor that is Faraday's constant over RT, so we can rewrite in this way. And we can rearrange this equation as E equilibrium minus E naught dash is equal to the RT over number of electrons transferred into Faraday's constant, and the log natural of concentration of the oxidized species in the bulk over concentration of the reduced species in the bulk. So here we have a form of the Nernst equation, that is E equilibrium is equal to the standard electrode potential at equilibrium plus RT here at the equilibrium. We have supposed that the current is 0, that is actually equal to the difference of current, cathodic current over and anodic current. Here we are not saying that no current is generated, but actually the current cathodic and anodic currents are generated, but they are equal in opposite directions. That's why overall current observed is 0. As the overall current is 0, but the cathodic and anodic components are not 0, but they are opposite in direction, so we can say that one of the component is equal to I naught, that is known as exchange current. Now again consider above equation, which is showing the total current is equal to the difference of these two factors with common factors given here. So here when we are taking the equilibrium condition in which the net current is 0, so this equation is modified as here. This equation is the total current equation, which have been derived from the Butler-Ulmer model of kinetics, that is electrode kinetics, which is expressing the contribution of the cathodic and anodic current. So when we have considered that the cathodic and anodic currents are equal and overall current is 0, so the each component, either cathodic or anodic, is equal to I naught, that is known as exchange current. So here we can write the above equation, which is expressing the equation for total current. So it cannot be equal to 0, or can be equal to 0 depending on the condition. This is the equation which is applicable for 0 or non-zero currents. So this equation is modified for the 0 current condition when the cathodic and anodic components are equal and total current is 0, but the I naught, that is the exchange current, is not equal to 0 but equal to either cathodic current or anodic current. For this condition, we have changed the contribution of the oxidized and reduced species at the surface into bulk species, and for equilibrium, this factor, that is contribution for the cathodic current, is rewritten as this factor, in which E have been changed to E equilibrium, and this factor is equal to the factor given here, in which Cr have been changed to Cr star, that is the bulk concentration, and E is changed to E equilibrium. It means that the bulk concentration and the surface concentration are in equilibrium. So overall the total current is 0, but the exchange current or the either anodic and cathodic currents are not equal to 0. Now let's consider exchange current for either component. Like I'm going to take the first one, that is the exchange current equal to NFA K naught C naught star minus alpha NF over RT E equilibrium minus E naught. So this term is the exponential term, and let's consider the expression we have derived earlier by equalizing the cathodic and anodic component for the equilibrium condition in which the surface concentration is in equilibrium with the bulk concentration. So this factor is equal to the power term. So by multiplying this power, this whole equation with minus alpha in the power, we get the expression given here. So here we can see that the term I have considered for the cathodic component, that is actually equal to the anodic one. So here this factor can be replaced with the factor given here, that is the ratio of the concentration of the oxidized species in the bulk over the concentration of the reduced species in the bulk raised to power minus alpha, that is the transfer coefficient. So by comparing these two equations, we get the modified term for exchange current. Now again we can simplify this equation as written here. So here we have changed this power C naught star is power 1, and here is minus alpha. So we have overall power is 1 minus alpha, and here we have Cr star is in denominator, so overall the power will be alpha. So here we can see that I naught is the exchange current that is proportional to the standard rate constant, and in the case when the concentration of the oxidized species equal to the concentration of the reduced species in the bulk, that is the simple concentration, so the exchange current will be modified to a value that is NF K naught into C, that is the concentration of the electroactive species. Practically the exchange current is usually expressed in terms of current density, which is known as the current over per unit area. So we have the final expression for the exchange current density, that is equal to the NFA K naught C, and this one is the important equation which have been used for the electrode kinetics.